Good morning, everyone.
Good morning.
Just in case you don't have it up already, there's link for poll everywhere. Got a minute though. Get my phone. Cool. All right, so I've got 8 o'clock. There's the link one more time, and let's go ahead and do today's daily quiz. So again, it's just about finding those potential rational roots, what we were talking about yesterday. And I just want to be clear again, like yesterday, we saw that we always have pretty much either the positive or negative values will work as potential roots. That's a little bit hard to type in. So we're just going to assume when you're typing in your answer, you're including that plus minus. Okay, but our goal for today is to find the list of potential rational roots for the polynomial x to the fourth plus x cubed plus x minus 8. So type in those numbers that are the potential rational roots. We're not trying to find the roots. Just list the potential rational roots. So x to the fourth plus x cubed. Saw a couple of people join at the last second. Let me get. I'm still screen sharing. And I'm still screen sharing. No, I'm not. There we go. That's what I'm looking for. All right, so here's the link one more time because I saw a couple people come in last second. I'm gonna give you all till 8:04, which is 45 seconds from now. 40 seconds from now, sorry. 40 seconds from now to finish entering your response because it looks like we got most everyone in already. It's weird seeing the same weirdly typed answer as well. Interesting. All right, so you've got, I think we got most, let's see, we've got 19 people here today. Awesome. and 16 responses. So we're missing 3 responses. You have 10 seconds to type in your response. 10 seconds. 5, 3, 2, 1. Locking answers now. All right. Well, it looks like everyone got the right answers. There was a couple that are just weirdly tight, but I think you're conveying it. So let's just go through it really quickly. But the answers would have been plus or minus 1, plus or minus, well, where'd that line come from? Plus or minus 2, plus or minus 4, and plus or minus 8. Because when we find our list of potential rational roots, we have all combinations P over Q, where P is a factor of your constant. So a factor of -8, and factors of -8 are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Pretty much anything that can divide 8, and then I got to make sure I consider both the positive and negative. And then that Q is the factors of my leading coefficient. Well, I just have an x to the 4th, which means my leading coefficient is a good old 1. It means its factors are just plus or minus 1. Those are the only things that will divide 1. So I take every combination of each factor on top divided by the factor on bottom. And as we saw yesterday, when we have this nice division by 1, it really just says, okay, potentially change the sign or keep the same. That gives us the list plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So when you typed in your answer, you should have had the numbers 1, 2, 4, and 8. And like I said, when you hit submit, we're assuming that you're answering plus or minus. Okay. So any quick questions before we begin? Because I think everyone got that. Thank you, Ashley and Leah, for giving me thumbs up. And Allie and Ron now. Chantel and Janelle. All right, yeah. So for those of you hitting the thumbs up button, wait a sec. Give me a thumbs up if you're here listening to my voice. You didn't just step away. Cool, got most people. Lost one, I think. Nope, we got the same, never mind. All right, so today we're gonna be talking about rational functions. And rational functions are just a polynomial divided by a polynomial. That's what we mean by a rational function. It's just some polynomial divided by a polynomial. So examples, x squared plus 2x plus 1 divided by x to the 4th minus 1. That would be a rational function because if I look in the numerator, I see that I have a polynomial, and if I look in the denominator, I see that I have a polynomial. And one of the things with rational functions is that they have an interesting type of behavior that we don't see with just regular polynomials. It comes from this possibility that what I see in the denominator could potentially be 0. One of the things we've been solving for, right? That's what we did yesterday, is find out when polynomials are going to be equal to 0. Well, if I throw a polynomial into the denominator, that means potentially that polynomial could be 0. And can I ever divide by 0? No, right? If you somehow find a way to divide by 0, you'll probably win a Nobel Prize and make the world blow up at the same time, right? It just can't happen. We can never divide by 0. So we get this interesting behavior around when that polynomial in the denominator is going to be 0, and that's what's called the vertical asymptote, right? That what you were watching that video on, and how to find. I won't be able to fit asymptote. Let me rewrite that. Vertical asymptote. It's just these occur whenever your denominator is equal to 0. I'm going to just short denominator to denom. And there's this interesting behavior that when, oh, we already did lose 2 people. I knew people were just going to show up to take the quiz and leave. Anyway, this occurs when the denominator is equal to 0. And when we have this, when we're dividing any number, let's say something like 3 divided by 0, obviously we can't do it, but what we're saying really is that what's happening in the denominator is getting closer and closer to 0. So it'd be something like 0.01. Well, if I actually calculate this value, this is what, 3 divided by 100, so this would be 300. If I got even closer to 0 in that denominator, so let's say divided by 0.001, this would be 3,000. If I got even closer, I'll write it up here in blue to try to just differentiate it a little bit. This would be 30,000. So we get this behavior that as long as I can figure out how I'm going to 0, I see that my numbers are going to be getting bigger in this case, but another option is if these were all negative, so I ended up getting values really close to 0 but below 0, all of my overall values would be negatives as well. But I get 2 types of dependable behavior. Either I see my values being unbounded and going up, or unbounded and going down. And then unbounded and going up is what we call that infinity, the positive infinity. Unbounded number in the positive direction. And then negative infinity is similar idea, unbounded number, but in this case, it's in the negative direction. Okay. So we find these values for these rational functions that are going to either make, as we get closer and closer to that specific value, or they're going to just keep going up and up and up and up, or we go down and down and down and down. That's why whenever you see people sketch graphs of those vertical asymptotes, like the lady did in the videos that you were supposed to watch, if I had a vertical asymptote at this point, I could see my behavior of my graph act something like this. As I get closer and closer to that blue dotted line, I can never cross it, because if I try to hit that blue dotted line, that means I'd be able to give my function this value, but this vertical asymptote up here where the denominator is going to be 0, I can't give it this value because I get a 0 in the denominator. And I could also see behavior like that. Okay. So this is why we like to study, because this is an interesting behavior and something that is pretty unique to rational functions. Okay. And also, if you find the right application, you can get where vertical asymptotes appear in real world problems. I know the book has got a couple at the end, but I just really wanted to focus on you being able to identify this, also horizontal asymptotes, and then we'll move on to the more interesting functions that describe the real world, which are exponential and logarithmic functions. We'll kind of get some more applications there. Okay, so you're going to have a new question on poll everywhere. And one of the things we do is, because we have this potential for zeros in the denominator, we want to make sure that we remove those values from our domain. Okay, so with rational functions, not only are we spotting vertical asymptotes, horizontal asymptotes, and also what are called holes, all of that is intertwined with the domain. So I'm giving you a rational function here. Let me share my screen, just so we get it for the recording. So what is the domain for the rational function f of x is x3 over x squared minus 5x plus 6. I'm just giving you the options here. And remember, we always, when we find domain, we just remove those problem points. In this case, it's where our denominator is 0. We don't want to include those in our domain. So I'll just give you a minute and a half about from now. Sorry to see some people selecting their answer. right, and like always, make sure you at least give me your best guess. Okay. I know some of y'all are still working. That is fine. I'm just saying, at least give me your best guess. All right, I'm gonna give y'all just 15 more seconds. We're only missing a few responses. I'm missing a few, 3 to be specific. So 10 seconds to select your answer. 5, 3, 2, 1. I'm gonna lock answers now. All right, so 67% of y'all got it correct. It is that third option. It is that third option. So one of the things to remember, especially if you chose the very last option, is that when we're talking about a function, this function, we're talking about x minus 3 over x squared minus 5x plus 6. Not the reduced form, which you can find. We're talking about this specific function. Okay, so I want to find when that denominator for this function would be equal to 0. So again, f of x is x minus 3 over x squared minus 5x plus 6. Our goal is to find that domain. So I want to figure out when the denominator is equal to 0 and remove those points. Well, I can factor that polynomial in the denominator. That'll be an x minus 3 times x minus 2 equal to 0, which means then that x has got to be either 2 or 3 for that denominator to be 0, which means those are the points that we want to remove because we don't actually want the denominator to be 0. So we need to remove 2 and 3, and the way we do that is we say, okay, then I can start out as far left as I possibly want and even farther. There's no bound to how negative I can go. And I can use all x values up to the first one that I have to remove. Well, the first one I'd come across if I'm coming from the negative numbers would be 2. So I'm going to get to 2. I'm going to skip over 2. Remember, that's what those open parentheses mean. I can get as close to 2, but not actually hit it. And then I keep going on, going on, and going on until I hit to my next triple point, which is 3. I get as close to 3 as I can from below. I skip over it. I can get as close to 3 as I want to from above. And then after that, I just keep going. So this is what my domain is going to be. One of the reasons we like to also identify the domain is then we know that at those 2 points, we write it in blue here, at x equals 2 and 3, we either have those vertical asymptotes. I'm going to use VA for short for vertical asymptote. So we either have a vertical asymptote or a hole. Okay, vertical asymptote or a hole. I don't think, maybe I didn't describe it before. I know she just mentions it in the video. It doesn't talk about it too much. What we mean by a hole in our graph is if we just had some function, let me do it in, let's say green this time. It's going to be a new color. So this is the graph of my function. A hole is essentially saying at one particular point, it's not defined. Everywhere close around it, everywhere close to this point right here, whoops, I can get a nice little arrow drawing to it. That's kind of an arrow. That is our hole in the graph. Essentially, I'm working well, I have a nice little solid line, but then I have to remove one particular point. Right? And that's where we, again, use that open circle to denote that. So we know at either at 2 and 3, we either have a vertical asymptote or we have a hole. What some of you probably did on accident was find where the vertical asymptote is, but guess what the next question is? Now that we know where our trouble points are, we want to be able to classify. Okay, so if you go back to poll everywhere, I've got a new question for you. Okay, but really quickly, I know I just talked for a good bit, and I haven't heard anything from y'all, and it's 8 a.m. and I know if I don't try to keep y'all engaged, you're gonna get lost. So questions if you got them, thumbs up if you're still here, feeling good and listening to my voice. Since I have no cameras on today, I can't see anyone. We just keep losing people left and right. Cool. Got mostly thumbs up. Awesome. Yeah. Awesome. 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 So yeah, go back to poll everywhere, answer. And this time you got to type it in. Remember, with vertical asymptotes or holes, this is where we care about what is that particular x value. We're really considering a vertical line. When we write x equals, it's that nice little vertical line. That's what we're indicating. So that's what I want you to not only write your answer as in your homework, but also type in your answer. So where is the vertical asymptote for this function, x minus 3 divided by x squared minus 5x plus 6? All right, we'll give you all another minute or so. I'm going to say minute and a half to type in your answer. All right, loving the answers so far. Not all correct, but you're giving me answers. Some of you are making a mistake that I want you to make. All right, I'm gonna say we got in, we're missing what? 16, so we're missing just 3 responses. I'll give you all 30 more seconds to finish typing in your answer. All right, I'm gonna block answers here in 5, 3, 2, 1. Locking answers now. All right, so correct answer, which most of y'all got, is it's just at x equals 2. So again, vertical asymptotes occur when I get a 0 in the denominator, but it's unchecked. Right? I'm going to get this unchecked 0, and that's why when you watch the video on this stuff, they say then reduce. So factor reduce, and then find your zeros in the denominator. Because if I have a common factor on top and bottom, those factors are keeping each other in check. They're approaching zero, but they're always canceling each other out. So that's why we always want to look at the factored form of our functions, reduce, and then simplify. So we knew, just write it in green, we knew possible values of a vertical asymptote. We knew where they might occur because they were the 2 points that we removed from our domain. Neither of them might be a vertical asymptote, both of them might be a vertical asymptote, or one of them might be a vertical asymptote. I mean, yes, I already gave you the answer. It's a single one, but let's see why. So if I take this x minus 3 over x squared minus 5x plus 6, and I factor it, in the numerator, I still just have that nice little x minus 3. That doesn't change, but in that denominator, we had that x minus 3, x minus 2. So what's the common, I want to hear it from someone. What's the common factor that I have that's going to get canceled out?
X minus 3.
Yeah, x minus 3. Because I have a common factor in both the numerator and the denominator. Yes, as x approaches 3, both of those two things will be approaching 0, but their values are always canceling each other out. Which means, and this is one of the things I like to do, is say this last equality, whenever we cancel out factors, is that our original function is going to act like, well, 1 over x minus 2. Okay, it doesn't have an x minus 2 factor that in the numerator that's going to keep this in check. Which means then as x get closer and closer to 2, I'm going to have a 0 in the denominator and nothing balancing it out in the numerator. So my vertical asymptote is at x equals 2. And that's what we go through, and that's why in the video she said factor, reduce, and then spot where your denominator is equal to 0 after that. Okay. So questions so far. That's vertical asymptotes. That's how you find them. In this case, we only have vertical asymptote at x equals 2. Questions? If not, give me a thumbs up. Awesome, they're coming in, but slowly, but they're coming in. So people are there, awesome. So next question then is, at what x value or values does the function have a hole? The holes are where we have a value that's, we technically have a 0 in the denominator, but it's always being balanced out. That's why we get this idea of it acts like, but we have this one point that the original function can't use. Okay, so type in your answer. This is a particular x value. At what x value do we have the hole? And you should be able to reason yourself to an answer here. So for Zoom, all right, got some answers coming in. This one's more of a see who read the book, admittedly. Cool. I'm gonna give y'all just one more minute for the sake of time. I want to make sure we do at least one more example with identifying vertical asymptotes and holes before we move on to horizontal asymptotes. And again, give me your best guess. If you're unsure, give me your best guess. Help give me an idea of where you're at with this. All right, so give y'all 15 more seconds. Because I want to make sure we're moving on. So type in your best guess for me if you don't feel confident in an answer. But some answers that are coming through are really good. Yes, love it. Some people are giving me their best guess. All right. I'll lock answers here in 5, 3, 2, 1. Locking answers now. So come back to Zoom for me. Thank you, Shamar, for putting it in. There's the link, just so you can hopefully get it up. Okay, so again, I'm going to say, remember this thing that I said at the beginning of all of this. If you didn't remember, that's fine. But I get to say that because I'm a teacher. We, at the very beginning, when we identified what our domain is, we indicated where either vertical asymptotes or holes are going to appear. We only had 2 options. Those 2 options were when x is either 2 or x is either 3. Because those are the points that make my denominator 0. And then we identified that at x being 2, we had a vertical asymptote. So if x being 3 is an issue point, it's either got to be a vertical asymptote per hole, and we said it's not a vertical asymptote, then, well, the answer's got to be that when x is 3 is where we have a hole. But why? Well, it goes back to that acts-like equality that I talked about before. We had our initial function, which was x minus 3, and I'm going to go ahead and give the bottom in factored form. X minus 2 times x minus 3. And then we said, okay, well, I have a common factor balancing each other out in the numerator and denominator. What was that common factor? Someone please unmute themselves and tell us.
X minus 3.
Yeah, that x minus 3. Because yes, as x gets closer and closer to 3, I would see that I'm getting something that's going to 0 in the denominator. That term x minus 3 is going to 0 in the denominator. But not only am I dividing by whatever that number is becoming, I'm also multiplying by it. And that's why whenever we multiply and divide by the same thing, they're just canceling each other out. So no matter how small that x minus 3 term, how close it gets to 0, you're also going to be multiplying by that exact same value. They cancel each other out. And that's when we get that type of behavior where, okay, as x approaches 3, it's really just going to act like 1 over x minus 2, because the x minus 3s are balancing each other out. But if I'm considering my original function, I still can't ever plug in the value being 3 because I would still get a denominator in, or 0 in the denominator. So anytime we have a factor cancel out in both the numerator and denominator, that is where we have a hole. So we have a hole when x minus 3 is equal to 0, which means we have a hole at x being 3. And some of y'all even went the extra step and figure out exactly where that hole has got to be, because I can plug 3 into here to figure out what it should be approaching. And if I did that, you would see that the hole occurs hole is at the point 3, 1. But all I was asking for in this problem was just what is the x value. So if you typed in x equal to 3, that's just what I was looking for. If you typed in the point where the hole is occurring, took it an extra step further, which is amazing. Okay. So I'm going to give you all a second to write that down, but I'm going to pull up the graph here so we can actually see the graph of this function and see where this hole is occurring and where that vertical asymptote is. But any questions so far? Well, I let some people finish writing this down. If not, give me a thumbs up. Yeah, thank you, Leah. All right. It's a scattering, but I'll take it. All right, let me get the up. So here is the graph. Let me turn it into projector mode, get those lines a little bit bigger. So this red line is that graph of that function, x minus 3 over x squared minus 5x plus 6. What we see is that when x is 2, we have this vertical asymptote. And I can see that as I get closer and closer to this vertical asymptote, right, I see my values going down to negative infinity if I'm coming at it from the left, in this case, positive infinity from the right. That's something you can test for, but we're not going to go through that. I just want you to identify where these are going to occur. As I can see, if I just keep zooming out, that red line, they'll end up getting closer and closer to where that vertical asymptote is. Let's try to zoom in maybe way up here, right? It just keeps getting closer and closer and closer, but never actually reaches it. And that red line just keeps shooting up towards positive infinity. The closer it gets to that blue line, the faster it goes up to positive infinity right here. Okay, it's a little messy now, and then negative infinity if I'm coming from the left, but we see that same type of behavior. It gets closer and closer and closer to it without ever actually reaching it. Okay. And then we also see when x is 3, it's not marked here, but this is 3 because 1, 2, 3. And when my y value is 1, I have a hole. Because the function can act normally, it's being well behaved around 3 because we have that common factor in both the numerator and denominator constantly canceling each other's out. But when I try to plug in 3, I would still get a 0 both in the numerator and the denominator, which if that would happen, the world would blow up. So we can't do that. So that's why we put a hole there. That's value is approaching. And that's actually a calculus concept, this idea of approaching, but we can never actually obtain it. So that's where that hole is occurring. This is what the graph would look like for it. Okay, so again, really quickly, questions if you got them, thumbs up if you don't. You want to just move on. But please, please, please ask questions. It helps. Also helps keep you awake and attentive at 8 a.m. in the morning for a math class. All right, I'll take the C of silence and mute icons, meaning that you are good. All right, so next question. So again, this time, new function, I'm just wanting you to identify the vertical asymptotes in this case. So I want you to identify the vertical asymptotes for the function. Let me share it to Zoom. So it's this one right here. We have 3x squared minus 3x minus 6 all over x squared plus 3x minus 10. So in this case, I want just the vertical asymptote or asymptotes, if there's more than one, for this. Right. So I'll give y'all, let's say 2 minutes to do it. Hopefully I'll give you enough time to write it down, factor it, and type in your answer. If not, at least get to the answer. I just want to make sure we also talk about horizontal asymptotes before I head out. All right, good answers coming in so far, y'all. Again, I know 2 minutes is not a lot of time. I'm just trying to make sure we're moving on. So I'm going to give you all just 30 more seconds. At least get to an answer. If you don't have time to type it in, that is fine. I would love for you to type it in though, so I get a good idea of where we're at. But make sure you at least get to an answer on your own paper. All right, I'm going to lock them here in 10 seconds. 5 seconds. 3, 2, 1. Locking answers now. Okay. No, not everyone was able to get in their responses, but it's at least the same people who responded to the last question. But the answer, most of y'all got it correct. It should be when x is -5. So again, to find vertical asymptotes, we factor, reduce, and then look at where that denominator is equal to 0, because we don't have any factors keeping in check, i.e. where we would have a hole. So I need to factor 3x squared minus 3x minus 6 all over x squared plus 3x minus 10. In that numerator, I see I have a nice little common constant factor of a 3 that I could pull out. That'll leave me with an x squared minus x minus 2 in the numerator. And just taking it a step at a time, I'm going to leave that denominator alone for the moment. But now I see the two polynomials. If I stare at them for a little bit, I can see that I can factor them. In that numerator, it'd be an x minus 2 and an x minus 1. And in the denominator, it would be an x plus 5 and an x minus 2. And then I look for, okay, is there a common factor in the numerator and denominator that get canceled out? That'd be when x is equal, or that x minus 2 factor, i.e. when x is equal to 2. So those cancel each other out, and I'm left with 3 times x minus 1 over x plus 5. So now that I've done this reduction, I've done this little axe-like equality. I can figure out, okay, when that denominator is equal to 0 is when I will have a vertical asymptote. So the vertical asymptote would be at x equals -5. Now it would also have to be a point that I remove from my domain from the original function. And then really quickly, I want someone to please unmute themselves. Where would I have a hole? Where would I have a hole? X equals what? All right, well, what was the factor that we canceled out, everyone? What was the factor that we canceled out in both the numerator and denominator?
2.
That x minus 2. Right, because that was the 0 that would have in the denominator, I'd have an issue with it, but the value is always being balanced out with what's in the numerator. So x minus 2, when that's equal to 0 is where I'll have a hole because I canceled out that common factor in both numerator and denominator, which means this is when x equals 2. Okay, so I'll have vertical asymptote when x is -5 and a hole when x is equal to 2. You weren't asked about the hole. I was asking about the vertical asymptote, but I wanted to make sure that y'all were able to answer hole as well. So any questions? If not, give me a thumbs up. I know most of y'all got the vertical asymptote question correct. Ooh, thumbs up. I see the thumbs up. Awesome. All right. So last thing we're talking about is horizontal asymptotes. And there's not a lot of calculation when it comes to identifying horizontal asymptotes. Okay. It's really just about there's not a lot of calculations. It's all about identifying. And it always depends upon the degree of your numerator and the degree of your denominator, the degree of top and the degree of bottom. Okay, and we always have these, we're always going to have three cases. When the degree of top is greater than, we're going to have another one when the degree of the top is less than, and then when they're equal. And in each of these cases, it tells me where my horizontal asymptote is at. If the degree of the top is greater than the degree on the bottom, that means I'm going to be getting larger and larger values as time goes on. So there is no horizontal asymptote whenever the degree of my polynomial is greater on top. My y values will not be leveling out to a specific value as my x's get larger or smaller. Whenever the degree of the top is less than the degree of the bottom, you always have a horizontal asymptote at y equals 0. And when they're the same, it is the ratio of the leading coefficients for both the numerator and denominator. So the first two examples, once you can identify the degree of the top and the bottom, pretty easy to see. That last one, I want to make sure that we can calculate. Again, I know she goes through it in the video, right? So again, I want you to be watching those beforehand. But if you go to Poll Everywhere, you have our last question for the day. You are given, let me share it. Oh, I don't want to share it because I'll lose this. Let me write, can I write it somewhere? I'm going to write it down here in the bottom left in green on Zoom, just so we can leave this little chart up. You're given 2x cubed plus x minus 1 all over 6x cubed minus 11x squared minus 13. In this case, we're just wanting to find the horizontal asymptote. As my x's get larger and larger, as they go to positive infinity or negative infinity, is this approaching a particular value? Okay. So again, you have to identify the degree of the new polynomial on top, the degree of the polynomial on bottom, and then once you have that identified, figure out what the horizontal asymptote is going to be. In this case, it's going to be a y value. That's why you write y equals something. So, don't really have time. If you want to listen, just passively listen, finish the work on your own, that is fine. If not, just come back to Zoom so we can make sure we're out of here by 8:50-ish. So we're wanting to find the horizontal asymptote for f of x, which was that 2x cubed plus x minus 1 all over 6x cubed minus 11x squared minus 13. So I need to figure out what is the degree of what's on top and the degree of what is on bottom. So I'm looking at that 2x cubed plus x minus 1. What's its degree? What is the degree of that polynomial? Someone tell me.
3.
Yeah, thank you. It is degree 3. And in the new denominator, I have a 6x cubed minus 11x squared minus 13. And what is the degree of that one? Little baby. Sorry. I just saw one of my nephews the other day. It reminded me of that. So what is the degree of the polynomial on bottom?
3.
3 again. So then once the degree of the polynomial on top and bottom is the same, we said it's the ratio of the leading coefficients. So I identify what is the leading coefficient for my numerator of my rational function. I identify what the leading coefficient is for the denominator of my rational function. So I see it's a 2 and a 6, which means my horizontal asymptote is going to be at y equals the top leading coefficient dividing by the bottom leading coefficient. So if you're at 2, 6, you're technically correct, but you can simplify 2 over 6. It simplifies down to 1/3. So this function will have a horizontal asymptote at 1/3. So if you graph this thing, as your x values get larger, so go to the right on the x-axis, as they go far to the left on the x-axis, both of these are going to be going towards approaching this value of 1/3. Okay. So I'm at 8:50. I know if you got questions, more than welcome to ask. If you're feeling good, you think you got this stuff, and you've stuck with us until the end of class and didn't just leave like some people did, all right, give me a thumbs up before you head out. Again, please ask questions if you got them. Oh, actually, before y'all leave, just so I don't have to do a reminder, I'm going to send one out on Blackboard as well. Remember daylight savings time changes. I think most of y'all are on St. Croix or somewhere in the Virgin Islands already, so you don't have to worry about this. But if, let's say, you're in Eastern Standard Time, Central Standard Time, whatever, something that is affected by daylight savings time, our class time is always going to be meeting at 8 a.m. Atlantic Standard Time, AST. So 8 a.m. for the time on St. Croix. So just be aware of that. That change is going to happen next week. If you live on St. Croix, nothing's going to worry you. You're still meeting at 8 a.m. But just want to make sure people are aware of daylight savings time, and we're meeting at 8 a.m. AST. So if you got that and you got no questions for me, you're good to go. Thank you, Shamar, for the thumbs up. All right, I'm going to stop the recording now. Thank you, Mona Lisa, as well. Janai, thank you. Can't see your faces, so that's the best form of feedback I can get. So thank you all for doing it.